I would like to start with acknowledgement to the country. We would like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. With that, let me welcome you all to the event. And at the very beginning, I wanted to give you a very brief overview of the PaCER program, and then I'll go into the introductions of speakers we have today. So Pawsey Centre for Extreme-scale Readiness, PaCER, is Pawsey's response to the unique opportunity to help researchers achieve superior scale on next generation supercomputers. The focus of PaCER program is on both extreme scale research, so that's on algorithm design, code optimization, application and workflow readiness, and using the computational infrastructure to facilitate research for producing world-class scientific outcomes. PaCER provides researchers with an opportunity to optimize their codes and workflows suitable for next generation supercomputers and Setonix, which will be Pawsey's next supercomputer. It is designed as a minimum 3-year partnership for collaboration between universities, research institutions, Pawsey, and HPC vendors by providing early access to supercomputing tools and infrastructure training, exclusive hackathons focused on HPC performance at scale. PaCER projects are also provided with co-funding for PhD or postdoctoral positions to work on technical aspects of their projects and build supercomputing expertise within their groups. 10 research projects were successfully granted access to the first PaCER program, establishing Australia's research platform for extreme-scale computing. There are some amazing statistics and numbers to share behind PaCER. We have 10 projects, but 18 institutions involved, including US national labs and industry partners. We have 70 plus researchers involved, 10 plus Pawsey supercomputing experts supporting projects, and 10 plus new positions created to work on the technical aspects of those projects. Pawsey is hosting a series of seminars, was hosting a series of seminars throughout June, showcasing the first cohort of PaCER research projects. The fourth in the series focuses on radio astronomy today. However, recordings of previous sessions focusing on material science, CFD, particle and molecular physics will be available soon online. Before I introduce our today's speakers, a few opening remarks. Today's presentations will go for around 15 minutes, and we'll have a Q&A session after all the presentations are done. So please post your questions in the chat, in the Zoom chat. They might be answered during the session, but by Pawsey staff or presenters, or otherwise we'll get back to those questions at the end of the session. Okay, let's get straight into it. We have 3 talks scheduled for today, and it is my great pleasure to introduce our first speaker, Professor Melanie Johnston-Hollitt. Melanie Johnston-Hollitt is an international prominent radio astronomer working in the space between astrophysics, computer science, and big data. Melanie, former director of MWA Radio Telescope, is currently the director of the Curtin Institute for Computation, CIC, a knowledge accelerator based on the use of data science and high-performance computing aimed at producing better outcomes for research, government, and industry. In her 20-year career, Melanie has been involved in the design, construction, operation, and governance of several major international radio telescopes, including the Low-Frequency Array in the Netherlands, the Murchison Wide-Field Array MWA in Western Australia, and the billion-dollar Square Kilometre Array SKA, which will be hosted in both Australia and South Africa. Melanie was a founding member of the board of directors for the SKA organization. In particular, she led the science analysis pipeline design and contributed to the science data processor pipeline, which will be needed to extract knowledge from the vast amount of data the SKA telescope will generate. Melanie's research interests span the intersection between radio astronomy, signal and image processing, and big data analytics, and she leads both the multidisciplinary team of data scientists in the CIC and the galactic and extragalactic science team in the Curtin Institute for Radio Astronomy. Melanie, the stage is yours.
Thank you very much, Mate. That's a hell of an introduction. I should say I'm only leading the radio astronomy group until tomorrow in the Curtin Institute for Radio Astronomy. I've moved on to now be the director of the Australian Space Data Analytics Facility, which is also Pawsey and CIC and also WADSI running. So anyway, today I'm going to talk to you about our project Piggy, which is in fact building on this career that I've had looking at how we can better get information from next generation radio telescopes. So the acronym stands for Parallel Interferometric GPU Imaging. And this is a project between the Curtin Institute for Computation, Pawsey and the University of Toronto, and the team members, which they've called themselves piglets. Myself, Torrance Hodgkin, who will be funded through the PaCER funding to start a 2-year postdoctoral fellowship in September working on this project. Luke Prattley from the University of Toronto and Ugo Varetta, among others at Pawsey. So I'm going to give you a bit of a history about radio astronomy to explain what it is that we're trying to do and the context behind that. So radio astronomy commenced in the late 1930s, and so it's existed for about 80 years. Importantly, in the 70s and 80s, there was a peak in infrastructure investment that happened on a national level and resulted in the construction of several major interferometers. So examples of this included the Westerbork Synthesis Radio Telescope in the Netherlands, the Very Large Array in the US, and the Australia Telescope Compact Array here in New South Wales in Australia. Now, importantly, when the radio astronomy community started investing in these instruments, they actually also invested in the image algorithms to be able to extract data and knowledge from those telescopes. So all of the image algorithms that we use today in radio astronomy are largely based on the deconvolution methods that were produced in the early 80s. So those two things go hand in hand. You've got an infrastructure investment and you've got an algorithm investment to extract knowledge. In the last decade, we've had a radio renaissance. And so we've seen the start of this phase of renewed infrastructure investment, either with upgrades to existing telescopes or construction of entirely new telescopes. So again, those same national countries that were investing in radio astronomy heavily in the 70s and 80s have continued to do that. So the Dutch went on to build LOFAR, the low frequency array in the Netherlands, which opened in 2012. The Americans upgraded the VLA, and in Australia, we upgraded the compact array in 2010, and it's due to have another upgrade again relatively soon. The Murchison Wide Field Array, which as Marcin mentioned, I was the immediate past director of, was built in 2012, upgraded in 2017, and is undergoing an upgrade again now. Importantly though, this did not coincide with major developments in imaging algorithms. So a lot of the imaging algorithms that we're using are the ones that were originally developed for instruments which were considerably less data intensive. And that's really what this project is about, trying to address that gap. So to give you an example, the way that we upgrade the instruments is in two primary ways. So one is you increase the observational bandwidth, the part of the radio spectrum that you're collecting data for. So for example, the VLA went from a 50 megahertz spectral chunk to a 2 gigahertz simultaneously collected spectral chunk. And those new telescopes are also being constructed primarily at low frequencies, which have very large fields of view. So for example, the Murchison Wide Field Array, the field of view is 30 by 30 degrees. Similarly, ASCAP is, I think, 25 by 25 degrees. That's the other telescope up in the Murchison in Western Australia. And if you compare that to the previous generation of telescopes in Australia, such as the Australia Telescope Compact Array, which is about half a degree by half a degree, that's a big difference. Now, to illustrate that visually, I have a picture here on the right of Centaurus A. This is the nearest giant radio galaxy to us. So you've got a supermassive black hole spewing out electrons very close to the speed of light, which are accelerating in a magnetic field and producing radio photons, which produce these huge big lobes, which are millions of light years across. This particular image was done on the compact array in a project led by Dr. Ilana Fayen, and I was in this project team. And the field of view of the compact array is about that. So that's 0.5 degrees on the sky. And so in order to create that image, we actually had to do a mosaic which needed over 400 pointings of the telescope. It took us 3 years to collect the observational data, and then it took I think, Tim Cornwell 2 years to actually process those data to produce that image. And this was published by Alana in 2011. We started the project in 2006. Now, with a telescope like the MWA, this is a single field of view. That's the same size image. And so you can see the huge difference in sky coverage that you get with these new generation of interferometers. This is 2 minutes of data taken with the MWA, produced by Ben McKinley, who works at Curtin, and reduced in a single day. So this is just to illustrate how much data we're getting with current generation telescopes. But wait, there's more. Because we're greedy, we continue to build larger and more complicated radio telescopes. And of course, the SKA, which Marcin mentioned in his introduction, is coming very soon. So this will be an instrument which will produce the highest resolution, fastest frame rate movie of the evolving radio universe ever. And as Marcin mentioned, there'll be 2 parts of this telescope, one part in Western Australia and the other part in South Africa. And if we look at the data rates for those instruments, they are quite impressive. So this is a graphic from the SK organization. It's a couple of years old now, but I think it illustrates the real increase that we've got in the data rates and the need to scale up to exascale levels. So on the right-hand side, you've got the mid-frequency telescope, which will be built in South Africa and comprise of around 200 dishes. It's going to have 2 terabytes of raw data per second and produce about 60 exabytes of data per year. Now, that's a fairly tractable problem. They seem like large numbers, but they're not really large numbers in today's term. But the low frequency component, which is going to be built here in Western Australia, will have around 130,000 dipole antennas arranged in stations of 256 each. They're going to be distributed over the Murchison Radio Astronomy Observatory area, and will produce 157 terabytes of raw data a second, or close to 5 zettabytes of intermediate data products a year. So that's 35,000 DVDs of data every second, raw data, that is. So that is a large scale problem. And one of the things that we're trying to do is to be able to deal with that data rate in terms of processing in real time and extracting knowledge as we need to, but also the challenges that you get from the fact that this will be a wide field telescope. So I want to talk a little bit about wide field imaging now and the challenges that we have doing that, particularly at low frequencies. So one of the things that we have with wide fields are they're so large that we can no longer approximate them as being flat in the imaging algorithms. So where you had previous generations of telescopes built in the 70s and 80s, those very small fields of view, we could assume they were basically flat, which helps with your imaging algorithm. With a field of view, which is substantially larger, you actually have to realize that you're doing projection onto a sphere. So you have to do spherical imaging. Secondly, the ionosphere distorts incoming waves. So stars twinkle, while radio waves also twinkle due to the ionosphere through similar effects. And that is not the same from one part of the image to the other. And obviously that gets worse the wider your field of view is. It also gets worse at lower frequencies. So this is a particular challenge for low frequency wide field telescopes like SKA low. So this leads you to have direction dependent corrections to fix the distortion of the plane waves as they come in. And of course, large fields of view have very large numbers of pixels. So this is an increase in the data just from the size of the image, not to mention the frequency coverage. So you obviously need high performance computing to process this. However, the traditional imaging techniques that we've had for radio astronomy break down and do not scale at the level that's going to be required. So the first thing you need to do is to come up with new imaging algorithms that can potentially deal with some of these wide field imaging challenges. And so we've been working on this for the last few years now, primarily Luke and I. And so this is just an extract of a paper that we published in 2019, coming up with a new imaging algorithm for W stacking and W projection. So that's dealing with some of these corrections that we need to make. So coming up with the algorithms is one thing. So that's step one. Step two, which is often missed, is actually making them efficient. So you need to then take your algorithm, deploy it onto HPC, and make it actually efficient and scalable. And we did this with the W stacking, W projection algorithm. We actually published the paper on the implementation and improvement details to put it on HPC. Now, step one can be done by radio astronomers, has to be done by radio astronomers. Step two generally can't be done by radio astronomers unless they've also got a very strong HPC background as well. And the number of people with both the required background in interferometric imaging algorithms and HPC is very small. I think I could probably count those people on my hand. Fortunately, for this project, we have 2 of them, Luke and Torrance, and so I'm quite excited about what we might be able to achieve through this Pawsey PaCER project. So there's also a human problem to overcome, which I just kind of want to point out here because I think it's interesting. So humans like to do things the way that they've done them previously. They don't necessarily like to change. And there's a number of sort of sociological studies which talk about this. So in addition to getting these better algorithms and their efficiency and implementation, which must be considered, radio astronomers tend to be so wedded to their traditional imaging processing techniques that rather than leverage the way that HPC architectures are working now and changing the way that the algorithms are structured, they'd rather mush the HPC to make it fit the algorithms, which is not really what you should be doing. So rather than that, we need to work with HPC specialists like Pawsey to ask this question of how can we improve scalability and performance using high performance computing architectures. So this is it's a human problem. It's completely tractable, and projects like PaCER give us the opportunity to do that, to bring these 2 worlds together. This graphic here, which I've used many times, is a little bit complicated, but basically it's showing you the evolution of image algorithm creation in radio astronomy for sort of 3 generations worth of telescopes. So that first generation of telescopes in the 70s and 80s, the current generation of telescopes like LOFAR and the MWA, and then the SKA. So you've got software efficiency from least to most on the x-axis. You've got software design efficiency from least to most on the right y-axis, and then you've got domain knowledge on the left, sorry, the right y-axis, left y-axis is the other, from astronomy to computer science, and then past to present on the top. So in the early days, you could have astrophysicists doing your image algorithms without much knowledge of HPC, and they were running standard implementations, 1 GB images, pretty straightforward stuff. Currently, we've got to be on clusters with parallel implementations. We need some knowledge of HPC, but for SKA, we're really going to have to up that HPC knowledge. So it's really this need to work together to scale these things up. So that's the context. So Piggy is a project where we want to take not the previous generation of image algorithms such as CLEAN. We want to use new reconstruction methods. So when you get data from a radio telescope, you get a signal which is an incomplete sky signal plus the telescope response. So you need to be able to remove the telescope response and structure that looks. So this has been done previously with deconvolution, but new techniques like compressive sensing, which is essentially a form of inverse problems, are providing really nice the telescope acquisition process, so the ionosphere, the wide field effects, and this is a massive computational burden, but then we need to actually be able to solve that. So this is an example on the right here of an observed radio image before deconvolution of the telescope pattern, and then reconstruction using a compressive sensitive method that Luke Prattley developed during his PhD. So standard modeling that we currently use uses image gridding and degridding processes, which is memory intensive for your interpolation kernels. And a new technique has been produced in the Netherlands called image domain gridding, which interpolates using fast Fourier transforms on GPUs. And so that actually computes the telescope model really quickly. IDG is really cool, but it hasn't been used with these new construction methods like compressive sensing. And so what we want to do in Piggy is combine the 2. So we want to take this IDG methodology to define your telescope and then use it in the new reconstruction models. And hopefully we can do that at scale on HPC. So we're going to implement IDG so that it can be distributed on a compute cluster first. So that'll allow us to leverage multiple nodes and increase the available computational resource and decrease the total runtime. And then we're going to make Piggy fly by combining it with the novel distributed image reconstruction algorithms. And we're going to use data from real telescopes to actually test it and validate it. So the ultimate aim of Piggy will be to deploy it on Setonix and use data from the MWA telescope in WA to validate it. And so that's the aim of this collaboration. Thank you very much.
Thank you so much, Melanie, for this great talk. Let me just remind you, because we've had participants joining during the presentation, So I'd like to remind that you're all welcome to ask questions in Zoom chat, and we'll come back to those questions at the end of today's session. And now it's my great pleasure to introduce Dr. Marcin Meyer. Marcin Meyer is an astronomer at the University of Western Australia with a range of research interests in galaxy evolution and the assembly of mass, angular momentum, and structure. His research focuses on surveys for neutral atomic hydrogen and the role played by hydrogen gas in the formation and evolution of galaxies. Marcin leads the Dingo survey, a project that will take deep hydrogen observations with the Australian SKA Pathfinder to understand how the hydrogen content of the universe has evolved over the past 4 billion years. In the lead up to this project, he was working on CHILS, a deep hydrogen survey being carried out with the VLA, as well as the wide field hydrogen stacking experiments in the gamma G09 field, also being observed with this facility. Marcin is a member of the SKA-HI Galaxy Science Working Group. Marcin, the stage is yours.
Great. Well, thank you very much for that introduction. So we'll just get underway. So like Melanie's talk, my presentation is going to be all about radio interferometric imaging, except taking a slightly, I guess, different flavor. And in particular, what I'm going to be focusing on is how we create the optimal images from deep observations with the SKA and its pathfinders. So this is observations that might last days, might last weeks, or might even last months. And as Melanie highlighted, this is a problem because interferometric imaging is computationally very intensive. We don't directly image the sky, but instead what we have to do is infer what the sky looks like from the Fourier components sampled by our telescope. So traditional methods will work for instruments like ASCAP shown here for short observations, so that might be 6 hours or 12 hours. But the problems really begin to set in when we take longer integrations, so for hundreds or thousands of hours. And that involves making some compromises, which, while they might be okay, we'd prefer not to have to make. And so this project is focused on developing a new methodology to hopefully overcome some of those problems. And in particular, as our testbed data set, we're using data from Dingo, which is this deep H1 survey happening on ASCAP. And in particular, this survey has a goal of understanding how the hydrogen content of the universe has evolved over the past 4 billion years and the role that material has played in the formation and evolution of galaxies. And for this project in particular, we're focusing on the relationship between H1 and the dark matter halos that those galaxies reside in. We have quite a large team working on this project, and in particular, I'd like to sort of acknowledge the work of Christoph Rozgoni here, who is a PhD student of Richard and myself, and he just handed in his PhD thesis last week, developing all the methods that we seek to implement now as part of this PaCER project. And we also have collaborators, of course, at Pawsey. Pascal's already up and running. The Oz SRC with Karen and Slava, Dan Mitchell at CSIRO, collaborators at Oak Ridge National Laboratories, and then finally Jeff Wagg at the SKA organization in Manchester. So for those not familiar with the nomenclature, H1 stands for neutral atomic hydrogen, which as element number 1 on the periodic table is quite fundamental to the assembly of mass, both in galaxies and of course, the universe as a whole. And this little diagram on the right here is showing the baryonic cycle of materials in galaxies. So starting off with the atomic ISM, which we can trace through the H1 observations I'm talking about, that then cools into molecular clouds, star formation regions, and then those stars eventually return their material back into the interstellar medium. So here I'm just showing a movie, which is another take on the importance of studying gas. So on the left, we have the material in stars, so the stellar population in this group of galaxies. And on the right, we have a representation of their gas, which is a part of what we're hoping to study with the H1. And the thing to take away really here is that these pictures are quite different. So we can never understand the full picture of the physical processes in these galaxies by studying one or the other alone. So we need to really both study what's happening to the stars as well as what's happening to the gas. And you can see here, finally, this evolutionary process leads to the formation of an elliptical galaxy on the right here, which is barely visible in the H1 content on the right. Okay, so historically, we've been able to observe H1 for quite a while now, but our samples of galaxies have really been very small, particularly when we look into the more distant universe, where we've only really had probably hundreds of galaxies that have been observed beyond the local universe, or a similar number of galaxies that have been studied in a well-resolved manner in the nearby universe. But this is all going to radically change with the development of the SKA and its pathfinders. And in particular, in this talk, I'm focusing on ASCAP, which is the new facility up in the Murchison region of WA, with its 36 antennas and 30 square degree field of view. And that's really what makes this facility unique, is this detector, phased array feed, which it has up here, you can see on the left. And what that detector lets you do is, rather than being able to image a single region of sky in one go, or beam, this telescope is able to electronically form 36 beams on the sky simultaneously. So we can image a region that's 36 times larger than we otherwise would be able to do. And that gives us a total field of view of around about 30 square degrees. And moreover, we're studying H1, which is a spectral line, and that also gives us redshift information, or an estimate of how far away that galaxy is. So when we take an observation, we not only get information about where the hydrogen gas is on the sky, we also get information in the third spectral dimension, telling us sort of effectively how far away that gas is. So we get these very large, very nice three-dimensional cubes from an observation with ASCAP. So the Dingo project is focused on carrying out very deep observations, so observations of 500 hours per field, and even up to sort of a couple of thousand hours per field. And we've chosen particular regions in the sky to study, which are very rich in multi-wavelength data. And on the right here is just a little movie showing where all the galaxies that we already know where they are from the Gamma survey. And in total, there's around about 300,000 galaxies that we already know where they are in the sky, and for which we can combine multi-wavelength data with our H1 observations. And this is just a very, very quick summary of the kinds of science that we're hoping to carry out with Dingo. As I mentioned, sort of a primary focus is on mass assembly in the universe, so how the total amount of H1 per unit volume has evolved as a function of cosmic time from roughly 4 billion years ago to today, and that's shown in this top right figure. But we really want to carry out a much more detailed study than that. So we want to know how the H1 is distributed between galaxies. So how many massive galaxies there are, how many low mass galaxies there are, and how that changes, for instance, as a function of environment, so whether the galaxies are isolated or whether they're in groups. And then, so just saying here, and as you saw in that movie earlier on, the gas content of galaxies can be very heavily affected by environmental processes through ram pressure stripping and the like, and it makes this material a really great tracer for studying those environmental processes and gaining a better understanding of what's happening there. And then finally, the third sort of category of projects that we hope to achieve is in the space of kinematics and angular momentum. So the 21 centimeter line can tell you the way in which galaxies rotate, and you can use that to calculate their angular momentum. And again, we want to use this survey to study how that's evolved as a function of time. Okay, so we have actually now got telescope time on sky, and we've carried out our first observations last year. And so this is just showing the huge field of view of ASCAP. It's not quite as large as the MWA field, as it was very nicely shown by Melanie, but still, for this kinds of science, it is huge. And so to give you a feeling, this image is roughly about sort of 12 times the size of the moon on each side. And each of these white little specks, if you could see them on the video there, is a galaxy. So we have just under 100 galaxies in this image. And I'm just showing some zoom ins here of 2 of those galaxies, which are nicely resolved in the data. So in the gray panels here, you can see the contours, which are showing you how the hydrogen gas is distributed. And then the grayscale image behind shows where the stellar population is. And you can see in both of these galaxies, they're not the same. You get a much more extended distribution of the hydrogen gas compared to the stars. And then for the second galaxy there, you can actually see the whole axis of the material is entirely different. So really telling you something about the physical process here. Is this a polar ring galaxy? Is it a very large H1? Is it a warped disk? And these are the kinds of things that we can learn about the history of the processes that happen for these galaxies. And on the right, I'm just showing the spectra, which is a consequence of these galaxies rotating. So the natural line gets broadened out here, and you get these 2 very characteristic double horn profiles, one due to the side of the galaxy that's moving away from you, and one of the galaxy moving towards you. So that's a little bit about Dingo. So what's the actual problem we're trying to address through this PaCER project? Well, for that, I need to give you a quick crash course in radio interferometry, and thanks very much again, Melanie, for helping me out in this space. Now, radio astronomy pipelines are much more complex than shown here, but I just wanted to introduce the 3, I guess, primary data products that are of interest to the work we're carrying out in this project. So the raw data coming off the telescope is a visibility, and that's produced by multiplying the time-varying voltages of 2 antenna pairs together and then averaging them over some cycle time, so typically a few seconds in the kinds of work that I do. Now, that doesn't, for a single antenna pair, that's a kind of manageable amount of data, but you have to do that for every single pair in your array. So for ASCAP, which has 36 dishes, you actually end up with 630 different pairs of antennas that you've got to carry out this calculation. And then moreover, for ASCAP, it's got 36 beams on the sky, so you multiply that number by 36, and that takes you up to something like 22,000 odd data products being produced every few seconds. So what you do with those data for one of those beams is you then take that visibility, and typically you would then place it on a grid, which is the middle panel showing here. And what happens is that as the Earth rotates, that changes the orientation of your antenna pairs with respect to the sky that you're studying. And your visibilities trace out these very nice sort of arcs in the space that you can see here as you carry out your synthesis, Earth rotation synthesis imaging. And then the final step you do is you carry out an inverse Fourier transform, typically with a fast Fourier transform for your grid here, to create your observed image that you want to use for doing your science. And I should also say there's also a bunch of kind of non-linear processing that you also carry out to try and get rid of the fact that you have this sparse sampling in the visibility domain. So there's many choices that you have to make in doing this process. There's no one solution fits all. And so typically you hold on to your visibility data and you iterate on this process until you get to an image that you're happy with. So if we look at the data rates for something like an observation with ASCAP, so this is for a single observation, your visibility data will be around about, so in this case, 39 terabytes. If you put that onto the grid and you carry out some compression, you get 9.1 terabytes in theory of data. And then if you invert that, you'll end up with quite a large product. Remembering we've got 36 beams. So in total, you end up with 47 terabytes, and then you mosaic all those beams together, giving you a final image of about 8 terabytes in size. For a single image, that's all kind of manageable. There's not a particular problem that shows up. The issue happens is that when for a survey like Dingo, you try and do this for all of your data. So now your visibility data products for the entire survey of Dingo is just under 50 petabytes worth of data. Your beam grids, so your gridded, yes, your beam grids are 11 petabytes. Your beam images are 60 petabytes, and your final mosaic data products for each of the daily observations is about 10 petabytes. So what that means is that for the survey and the default imaging, most of these data products just get deleted. It's not possible to hold onto them. So the raw data now is not stored. The grids are not stored. They're typically just an intermediate data product. The beam images aren't stored. The only thing that gets stored are the final daily mosaic images. However, this creates some problems in that your daily images, you carry out the best job you can on a daily basis, but there might be a lot of low-level systematics that are still present and which may impact your final science and indeed only become visible when you stack all of those daily mosaics together. So your errors get baked in, and because you've only held on to the final data product, it's very difficult to mitigate them post-fact. So instead, the model that we're seeking to implement in this project is to hold on to this intermediate data product that's typically thrown away, the UV grid, and instead stack those UV grids to create a deep final grid, and then invert that and a mosaic that product. And if I just go back one slide, you can see that these UV grids are actually very similar in size to the final mosaic images. And the reason they're relatively small is this fact that they're sparse. You've got a lot of white in the grid. It's all just zeros. So this is data you don't have to store or compresses very easily. And it's that fact we're seeking to take advantage of in this project. So we've now tested this. This is just showing a figure from Christoph's thesis and proving that we can retrieve a spectrum that's the same as that with the image stacking method. So it all appears to work very nicely. And again, here just showing some images of one of those galaxies I presented. And you can see here that the traditional visibility stacking method is shown at the top here. And with the UV grid method, we indeed achieve exactly the same image, which is very satisfying to see. And indeed, we do a slightly better job than through the image domain stacking method, which is the current default. So all of this, I think, is giving us a lot of confidence that this method will be useful. So now we've just got to go ahead and deploy it. We've carried out some initial tests here to see how much data volume we can actually save by storing the grid and making use of the fact that it's a very sparse data product. So here we took an original data set, which was roughly 5 gigabytes in size. Now, ultimately, we want to use a sparse storage methodology, but to start with, we're just using this Adios 2 storage manager that implements different compression methodologies underneath the hood, but still looks the same on the outside according to our radio pipelines. And when we use initially, we started with a couple of lossless compression methodologies, you can see that we achieve already just a factor of around about 5 to 10. So when you're dealing with data sets that are of order 60 petabytes in size, a factor of 5 to 10 is very useful. Now, one interesting thing is we also tried a lossy compression methodology, and it actually did no better than the lossless compression. And that turns out to be the fact that the lossy compressions actually just turned a lot of these zeros into numbers that weren't quite zeros. And so you didn't actually end up saving terribly much more using the lossy method compared to the lossless. So certainly from my perspective, I feel a lot more comfortable using a lossless method, but nevertheless, this is something that it's probably useful to explore. And that sort of brings me to the end. So I'll just leave these goals and milestones up here, but bottom line is we're seeking to deploy this new deep imaging radio astronomy pipeline for ASCAP and hopefully in the future the SKA.
Thank you very much, Martin, for this great talk and also this introduction to interferometry and in pipelines you are using. That was very useful. Now it is my great pleasure to introduce Dr. Marcin Sokolowski. Marcin Sokolowski is a research fellow at Curtin Institute of Radio Astronomy here in Australia. Marcin received a master's degree in physics from the University of Warsaw and PhD degree in physics from the National Centre for Nuclear Research in Warsaw, Poland, where he became an assistant professor working on software for the automation of wide-field robotic telescopes and algorithms for the identification of optical transients of astrophysical origin. In the last few years, Marcin has been looking for fast radio bursts, FRBs, and other transients at low radio frequencies using the wide field images from the MWA and all sky images from prototype stations of the low frequency square kilometer array. Marcin works in a large international team of engineers and scientists on verification, commissioning, and developing novel calibration methods for prototype stations of the SKA low to be built in Western Australia in the coming years. Marcin, the stage is yours.
Thanks, Maciej, for this very generous introduction. And also thank you, Melanie and Marcin, for introducing everything related to radio astronomy, MWA, SKA, ASCAP. And yeah, I will rely and pray on this during my talk. So welcome, everyone. My name is Marcin Sokolowski, and I work at Curtin Institute of Radio Astronomy, ICRAR. And today I will present PaCER project Blink. I will also introduce the team, but a bit later on. So the main goal of this project is to look for fast radio bursts in high time resolution images from the Murchison Wide Field Array, MWA, and also from the prototype stations of the low frequency component of the square kilometer array, SKA low. So I will start with a little bit of introduction into what fast radio bursts are, FRBs. So you've already heard a lot about radio astronomy, but not so much about radio transients and FRBs in particular. So these are very short millisecond radio pulses, which were discovered quite recently, less than 15 years ago. And the first FRB was detected with the Murray-Young radio telescope, also known as PARCS. It was discovered by Lorimer in 2007, who analyzed archive data from 2005. The telescope you can see in the image on the right. So this is a very big dish, and the first FRBs were detected at frequencies above 1 gigahertz. So this first FRB, image of this first FRB is shown in the image on the right here. And what you see here is the dynamic spectrum, which is often shown in the context of FRBs and pulsars. And you see here intensity as a function of frequency and time. So this black stripe across the image is the pulse, which, as you can see, arrives earlier at higher frequencies and later at low frequencies. And this time delay between arrival times is given by this equation at the bottom, and it's proportional to dm. dm stands for dispersion measure, and this is the integral of the electron density along the line of sight between observer and the FRB. And you can think about it also as number of electrons per unit area between observer and the FRB. So in order, typically what has been done to look for FRBs, we need to correct for this effect of dispersion. So to do this, we need to align signals at all frequency channels in time. So we have to apply appropriate time delay according to this equation at the bottom, such that we align signals arriving at all frequency channels to be aligned in time, and then we can sum the power along the frequency axis, and this process is called dedispersion. So this way we can create so-called dedispersed time series, which is shown in this insert image on the right. And then we can find, this way we can increase signal to noise ratio, and we can find peaks in this time series exceeding certain threshold of, say, 10 sigma, 10 standard deviations of the noise. So a little bit more about FRBs. After several years of studies, we now know that they are of extragalactic origin, and therefore huge energies are produced in these processes, so that we can see them as bright as they appear in our radio telescopes. They have to have energies of the order of 10 to the 39th ergs, and this requires coherent emission mechanisms. We still don't fully understand how they are produced, and therefore they are quite very mysterious and still await full physical explanation. We know that some of FRBs repeat, so these are known as repeaters. And first repeating FRB was discovered by the Arecibo radio telescope. It was FRB 121102. as I mentioned, first FRBs were detected at frequencies around 1.5 gigahertz, initially by Parkes radio telescope and later by ASCAP, and later refurbished Atmos radio telescope detected several FRBs at around 800 megahertz. Since a couple of years, the CHIME radio telescope in Canada detected many FRBs between 400 and 800 megahertz. What I would like to point out is that up until last year, there were no detections of FRBs below 350 megahertz. However, last year we had 2 publications. So one FRB was detected by Greenbike telescope GBT at 350 megahertz, and also we had publications from low frequency array LOFAR in Europe, and they detected repeating FRB 1809-16B at frequencies down to 110 megahertz. So you can see this multiple pulses from this repeating FRBs be detected by LOFAR in the image on the right, where you can see similar dynamic spectrum as before. The frequency is on the vertical axis, and you can see that emission from these FRBs in some pulses extends down to even 110 megahertz. So now we know that these FRBs can be detected at very low frequencies, even down to hundreds of megahertz. Also, last year witnessed first detection of FRB-like signals, radio pulses from galactic magnetar, and I am bringing it up because this was first observation like this. And these magnetars are actually one of the main candidates to be progenitors of FRBs. And magnetars are highly magnetized neutron stars with extremely large magnetic fields of the order of even 10 to the 15 Gauss. And so the hypothesis is that FRBs might be due to radio pulses from magnetars located in galaxies other than the Milky Way. So once in a while, they emit very bright radio pulse, which can be observed on Earth as an FRB. There are also other, as you can imagine, this theory is mainly to explain repeating FRBs, although possibly there are some hypotheses as well that generally all FRBs repeat. However, we can only observe the brightest ones. But there are also theories for single FRBs, for example, that this is due to neutron-neutron star merger events. So moving to low frequencies, we tried to detect FRBs during multiple surveys using MWA as well. So I will mention this one, which I was very involved in. In 2017 and 18, we tried to use MWA to observe the same field of view as ASCAP radio telescope. So we, so to speak, shadowed ASCAP field of view, and during its campaign to look for FRBs, over this time, ASCAP detected 7 FRBs. Unfortunately, only three of them were detected during the nighttime and during favorable conditions for MWA data to be of good quality. So we collected the data during when these FRBs occurred, and we knew the DM from ASCAP and the positions of these FRBs from ASCAP. So we formed images, half-second images in one coarse channel of 1.28 megahertz, and we did this process of dedispersion in image domain. We checked the position. Unfortunately, no low-frequency signals there, no low-frequency counterparts of these ASCAP FRBs were found. However, we were still able to derive upper limits on the fluence of these FRBs, and therefore obtain some constraints on physical parameters of the surrounding circumburst medium. For example, to constrain size of the absorbing region that was required to absorb all the low frequency signals. So here I am just briefly showing a summary of several other surveys. These are so-called blind surveys, which were looking for FRBs in large areas of the sky, not knowing where they are. And the first line in this table shows the survey by GBT, which actually detected 1 FRB. So this one had a field of view of about 1/4 of square degree observed for about half a year with a sensitivity of about 1.25 Jansky milliseconds, which is very good sensitivity. And I constructed a figure of merit such that giving me some estimate of the number of FRBs that we could detect, which should be proportional to the field of view that we are using, observing time, and divided by our time resolution, and proportional to the our sensitivity to the power of 1 minus 1.5, which corresponds to the Euclidean universe. And therefore, I can calculate this figure of merit for all the other surveys in the table, which are from LOFAR and MWA. And as you can see, and then I can normalize this to the value of this first survey, which detected actually 1 FRB over half a year, so potentially 2 over a full year. And as you can see, these earlier surveys have either a fraction of FRB per year to be detected, or maybe 1 or a few. And the last row in this table shows an all-sky monitoring system with an enormous field of view, which is of the order of 12,000 square degrees, and observing for a full year with sensitivity of about 200 Jansky milliseconds, it should detect about 140 FRBs. So these earlier surveys were not successful because of a combination of factors such as not sufficiently large field of view, not sufficiently long observing time, or lacking sensitivity. Like, for example, this survey was quite using 112-second images from the MWA, so not very sensitive. And here I listed some possible upgrades. So what you can see in this bold line here is upgraded survey by Dingo et al. In 2015, which used MWA, a field of view of about 600 square degrees, and time resolution of 2 seconds. If we would go down to a time resolution of 10 milliseconds, we would actually improve sensitivity by about order of magnitudes, sensitivity to FRBs. And this way we would also increase number of detected FRBs per year to about 60 per year, which is also about order of magnitude. So as you can see, this kind of wide field image-based surveys with high time resolution images like MWA in 10 millisecond image with 10 millisecond images, or all sky monitoring system in 10 millisecond images, can actually detect between tens and hundreds of FRBs per year. So that's what we want to do enable with this project. Basically to form very high time resolution images and look for FRBs. Because traditional methods of looking for FRBs by forming tide array beams and tiling it over entire field of view are quite computationally expensive and may take many, many hours of data processing. So therefore we'll try to form very fast, quickly high time resolution images of the order of 10 milliseconds or better. So this basically requires very fast imaging algorithms. And then we will look for FRBs in these images. As you can imagine, this poses a computational challenge, because if we form 10 millisecond images and we channelize them into, let's say, 300 channels, this will end up with about over 100 million images per hour. And then assuming these images are at least 600 by 600 pixels, we can end up with data volume of about 320 terabytes per hour, which is basically very hard to store permanently. So what we want to do is to analyze these images as close to real time as possible. Let's say if we can analyze 1 day worth of data in 2 days, that would be a great improvement from where we are now. And then for every direction in the sky or pixel in the image, we will form a dynamic spectrum similar to what I shown before, and we will look for this kind of dispersive sweeps as the one shown for this particular FRB detected by Parkes radio telescope. And for different DMs, these dispersion sweeps will be different. So they can be steeper or shallower. And therefore, we need to perform many DM trials to actually find these FRBs. So as you can imagine, this is a very computationally intensive problem. Other than that, MWA, we can also use the images, high time resolution images from the SKLO prototype stations. The 2 of them are shown on the left here. So one is the AAVS2, which is 256 Scala 4.1 antennas, Christmas tree antennas, as the one shown here. And the other is EDA2, 256 MWA dipoles as the one shown here. And these stations can actually form so-called all-sky images, which are basically images of the entire hemisphere, as you can see in the example on the right with a galactic plane shown here. So these images, if we can form 10 millisecond images, we can also look for FRBs in this kind of images. So here you can see a movie with 10 millisecond images from EDA2 station, just as an example, formed in 1 megahertz of bandwidth, and we want to do it over much wider bandwidth to look for these FRBs. So once we have 10 millisecond images, we will also fine channelize them. So we will have about, let's say, 300, 400 images in each frequency channel per one timestamp of 10 milliseconds. So as you can see, we will have a huge data cube. And then for every direction in the sky, we will again form such a dynamic spectrum like shown here. And this is the dynamic spectrum from the EDA2 station, where you can actually see a dispersed pulse, not very high signal to noise ratio, but this was actually a so-called giant pulse from a crab pulsar, which we can use for testing, because pulsars also once in a while emit very bright radio pulses similar to FRBs. And this was actually found using existing software, FREDA, which is also used by ASCAP to look for FRBs in ASCAP data. So with this project, we will explore the existing software and try to use it to look for FRBs in dynamic spectra from MWA or SKLO stations images, but we will also possibly need to develop new algorithms and new software for this. So there are technical challenges, and we would like to make the data flow as smooth and fast as possible. Currently, with the current existing pipelines, one of the main limitations is the amount of I/O operations. So for example, after every conversion step, the data are written to drive and then read again for the next processing step. So we'll try to avoid this. We try to keep data in memory, and ideally all the time in GPU memory, so that we avoid any transfers, even between different memories inside in the supercomputers. And then from this, we can form visibilities and form wide field images. And there are some computational costs related to this. Some algorithms can have lower costs, such as n log n. For example, EPIC algorithm can do this, but they have some limitations. They cannot necessarily be applied to wide field images from the MWA, maybe only from SKLO stations. So we will explore this and try to come up with the best solution, which we will be able to apply to both types of images. And then once we have these high time resolution images, as I mentioned, we have to form this dynamic spectra, and for each direction in the sky, do many DM trials to find FRBs in some DM range, let's say from 0 to 1,000. For example, brute force searches, complexity of this algorithm is proportional to number of frequency channels, number of time steps, and number of DM trials. There are better solutions, such as, for example, fast dispersion visual transform, FDMT, which instead of being proportional to number of frequency channels is proportional to the logarithm of number of frequency channels. So we will explore this, and possibly we will try to come up with something even better. So our team is mainly composed of researchers from Celtic Institute of Radio Astronomy, CIRA. So myself and Dr. Danny Price, we are from CIRA engineering group, and we work on software astronomy instrumentation, but also software algorithms and data analysis, and also for looking for fast radio bursts. And Danny is project scientist for the Breakthrough Listen program in Australia. So he is very interested in looking for extraterrestrial intelligence, both in MWA data and in future SKLO data. So we have expertise in processing high time resolution data streams and large data volumes. We have also scientists from CIRA Science Group. Dr. Ramesh Bhatt and Dr. Sami Makswimi are experts in PaCER astronomy and also FRBs, and they have very extensive experience in processing high time resolution MWA data. We already have one PhD student, Susmita Seth, who is using MWA images to look to try to find new pulsars. And we collaborate with Christian Di Pietrantonio from Pawsey. And most importantly, we are currently looking for a new PhD student who will undertake this challenge of developing this fast imaging algorithms to produce high time resolution images, and then develop algorithms and software to use these images to find FRBs in this data. And hopefully this will lead to detections of FRBs and lead to enable publishing these results later on. So yes, if you know such a person who is willing to work hard, who is very keen on high performance computing and GPU programming and would like to join the team and undertake these challenges, if you are such a person or you know, please get in touch with me. My contact details are below, and I will stop here and I will take questions. Thank you very much.
Thank you, Marcin, and thank you to all the presenters and participants of today's event. It was a great occasion to learn about your projects. As I mentioned, we were about to answer questions at the end. I'm also aware of time. We'll run a little slightly over time. So if you can, please stay online. Otherwise, we will try to address the questions asked via email. But yeah, let me just try to go quickly through some of the questions. The first was asked by Aditi. That was a question about what volume of data does 2 minutes of observations equate to, and I believe this was a question to your talk, Melanie.
Yeah, I actually don't know off the top of my head. It's not actually very big. It also depends if you mean the raw data or the image data. So the image that I showed there is about 1 gigabyte. I don't know what the raw data is, probably much less.
Okay, thank you. Because I know that we've seen in a couple of occasions that radio astronomers do use minutes or hours of data as a unit of data. Actually, that's what
yeah.
And I guess that this is actually related to a specific instrument that is being used for observations, right? So yeah, okay. There were a couple of other questions. The second one was asked by Mahinder. That was, as distances traveled in infinity, how do you interpret this in 3 dimensions and color? When it comes to black holes, how do you interpret the 3-dimensional effects? And that was, I believe, a question asked after Martin's presentation.
Right, yeah. So we're not directly studying black holes in our field of view. There is some interest about AGN and how that might impact H1 content. For the distances, I guess we're studying a finite volume that we're looking at. How you convert, say, redshifts to distance is that's not straightforward, but I mean, we typically just use the appropriate cosmological formula to do that calculation, or we can use things like Tully-Fisher distances or other methods to improve those estimates.
Thank you, Martin. And there was also some discussion in the chat about lossy versus lossless compression. And Richard actually mentioned that there are some new developments and latest results from ADIOS 2, which achieved lossy compression of about 2% of original size. That relates to 222 megabytes in this case. And that was promising. And there was a follow-up question from Pascal. Is this lossy compression with similar amounts of noise allowed?
Yeah, I mean, it's quite interesting. I mean, obviously some of these, it's great to see that result there, but yeah, we have to run tests to see how that potentially impacts the science quality of our data product, because obviously there's going to be a limit somewhere where you wouldn't want to do it. Lossless is fine. We'd probably have to carry out further tests on lossy, but it's a great result anyway.
if I may just jump in and make the comment that it's because we're talking about residuals, you would normally accept quite a large loss of accuracy because you're already down in the noise. But systematic errors are what's going to kill you in everything that's coming. Thermal errors are going to be inconsequential when you've got that much collecting area. And systematic errors are what's going to kill, I think, will be the ultimate limit of most SKA observations. So if these lossy compressions introduce systematic errors, you are cutting your own throat in a way that's unacceptable.
Thanks, Richard.
Thank you, Richard. There were two other questions that just came. So one from Dylan. I was just wondering how many hours these production pipelines take to run on the HPC systems, like, for example, your project, Martin.
We don't know the answer to that question yet. So we've just been really running this on doing single beam tests and on limited numbers of data just to prove the methodology. But the PaCER is exactly, we now have to scale that up and get the answers to some of those questions.
If I may jump in again, Martin, sorry. One way of counting it would be saying it will take 0 time, because this runs as a side product of the normal data reduction. So the ASCAP team will be doing continuum imaging and daily spectral line imaging. And if you accept that cost, this PaCER aspect of Dingo is no significant additional cost. So you can count it as 0.
It's not a real-time pipeline, so that's the advantage. Yeah.
Okay, thank you. And another question from Lachlan. Is it possible to separate processing, so correlation, removal of RFIs, etc., from analysis imaging, or will there always be compromises in terms of the produced raw data?
Possible. Was a short answer. So it depends on the pipeline that you're actually using, but for the MWA, for example, the RFI flagging process is distinct from the correlation process at the moment. So yes, it's possible to do that. I think most of the time we would be doing that. There might be a few cases where you try and put those things together in an optimization process, but I think generally they are separable. What do you reckon, Martin? Do you agree?
Sounds good.
Yes, what I was aiming for there is, so for example, in terms of Pawsey, we will be the processor, if you like. We're working on the SDP for SKA, and then the actual analysis that will, at this stage, would be done in the SRC. But as I've come to realize, each instrument is different. Plus, you have multiple different surveys, on each wanting a different data product. So is it possible to actually produce a data product that then is suitable for all your survey teams and is, optimal and is small enough for you to keep? Because, is it possible to have a separate data processing routine from all of your analysis, or are they're too interdependent, and it depends on what you're trying to do and the instrument?
Largely depends on what you're trying to do on the instrument. So if you take SKA low, for example, the EOR project, so looking at the epoch of reionization, they actually don't want imaging data. They want to take the visibility data and they want to tap it off at a higher level than the rest of the applications that we have. So there are data products that you can get which are useful for a large section of the population, a large section of the science that we're trying to do. But I don't think you would come to something which covers every single use case that you want. I mean, you've heard in these 3 talks, 3 very different use cases. So Martin's doing spectral line observations, so spectral cubes, basically. Marce's doing FRBs, so that's time domain, observations. And what I'm talking about was an imaging pipeline for continuum imaging, effectively, or polarization as well. So I think the short answer, Lachlan, is no. But I think you know, it's a question of how many edge cases do you want and where the responsibility for processing those things lie. So you think in the main, you'll have a standard data product for the majority of people, which will probably be a continuum / polarimetry cube. It's what we do now. Then you'll have an H1 type spectral pipeline, and then you'll have other things. They might not all be done in Australia, for example, for SKLO. They might not all be done at all for any particular telescope. So people have the opportunity in the SKA project, for example, to come along and say, I'm going to do this particular type of processing in China because the Chinese are interested in paying for a processing pipeline there. Does that kind of make sense?
Yeah, and I mean, that's, I guess, like I said, from Pawsey's perspective, trying to understand, you know, all of the fact that it isn't just, okay, we've got a processing pipeline, we're going to produce one, you know, product, and we've got one algorithm, and then we're going to give that and to go from there. It's the fact that there's not only just a lot of data, people want different things out of it, and they want to process it differently. So yes, it's complex.
Yep.
Okay, thank you. So there are more questions coming. I am aware of time, and but with this event, we are also trying to a little bit simulate the in-person event. So if you have to go, please, yeah, for other meetings, we understand. But if you can stay for some hallway discussions, please stay on the line, and I will just read a couple of more questions, or we'll try to address it. Also, and in this stage of this seminar, please feel free also to unmute yourself and ask your questions. But I will read the next question. So there was a question from Christian. Even with compression, it is still probably too much data to store in the long term, at least with today's resources, and to process in a timely manner. Do you see this challenge bringing several research groups infrastructure together to pool resources and coordinate effort? How will the new data rate affect the way you work?
Well, we're not going to be able to do any of this without pulling together resources that we've got. I mean, extracting the knowledge that we're going to get out of these data is a project that would, you know, probably consume the entire radio astronomy community in the world if we wanted it to, depending on how much knowledge we're trying to extract. So yes, in terms of how it changes the way we work, I don't think it does very much, because radio astronomy is highly international and highly collaborative. And so if you look at projects like the MWA or SKA, they're already using teams across the world to do this stuff and bringing resources together. So I don't think it'll change the way we work. I do think there's an interesting prioritization piece of work to be done. So which science do you do first, and what resources do you put into that? Do you go for something very difficult like the epoch of reionization, which is understanding when the first stars and galaxies form in the universe, and potentially get somebody a Nobel Prize, but is very, very difficult? Or do you go for the low-hanging fruit of suddenly going, oh my God, we've got this incredible instrument that's going to produce surveys at a depth and resolution that we haven't had before, so there's a whole bunch of stuff that will be new and easy to find? So I think that's an interesting question, which hasn't really been answered. We've talked about it a lot, but I don't think anyone's really answered it, because it's one of those things where I think when you get to the pointy end, you make those decisions. But yeah, no, radio astronomy is highly, highly collaborative and international. So definitely collaborate on this across the world.
Thanks for the answer.
And the next question was from Costa. Can the correlators be programmed to produce different intermediate data products at the same time?
Depends. Yes, theoretically, but that depends on the limitations of your hardware and your pipelines, and again, what you're trying to do.
And the last question I see in the chat, how do you validate the software?
Same way everybody validates software, I would imagine, through unit testing and comparison. I mean, one of the luxuries that we have is that we've got a suite of radio telescopes that we have been using on the path to the SKA already. And so, for example, when we're developing, say, the new correlator for the MWA, MWAX, which is the project that's currently undergoing, we have the luxury of comparing the output from the legacy correlator to the new correlator. And so doing a whole bunch of unit testing and other debugging and reality checks against an existing and validated pipeline.
Yeah, that's an interesting interesting discussion between the challenge to adopt to new technologies and HPC tools that you need to use on those new systems. But then if you compare that to the actual challenge of designing a completely new algorithm to work on something at scale, I guess for most of the projects, it's this challenge around design of the algorithm that is actually even more important for to tackle, right?
Yeah. So when we did the algorithms that I talked about in the talk that I gave, we had to again cross-validate that on data from existing telescopes using different imaging algorithms. And because you're actually incompletely sampling the sky, you can't really do it at 100%. So we also did it on simulated data as well, so that we could truly understand whether or not we were covering the signal that we expected. So there's a kind of a combination between those two things. Ultimately, it comes down to confidence and whether or not you can convince people that what you've done is actually giving them a result that they believe, which is again got a human element to it.
Yeah. There was also a question about how do IT giants collaborate with us. I think this is really something that I wanted to emphasize around PaCER, that it's a truly collaborative project, not only in the sense that we have various projects awarded within PaCER working together, because they very often have similar challenges, like here with the radio astronomy projects, but also across disciplines, which we find quite interesting that we can bring groups together to work on some specific challenges related to technology. And all those activities that we'll be building around PaCER will be available for others as well. We are collaborating with the vendors of HPC solutions and as well as software. And you will see a lot of activities around PaCER, so seminars, hackathons, trainings. Please watch that space. I think that completes the questions that we have received in the chat. Thank you, all the presenters and participants of today's events. Have a great rest of the day, and we hope to meet you soon again online or hopefully in person. Thank you all.